In this video, we learn how to model heat transfer from IC engine. IC engine consists of the header, and inside of the header has a number of the liner coated, and we have to model the heat transfer from the IC engine with liner, and this is a very simple problem we can model using CFD. An IC engine has a top cylindrical head, liner is around cylinder, and it helps to protect from the wear and tear of the piston. And here are some cylinder with a liner. You can see here is a liner around the cylinder, and there are multiple liners are there, and each has a thickness around 0.15 mm, and there are different conductivity and thickness for the liner. For this problem, liner has to be the same, and we can see further how liner is there in 2D sketch. And this is liner around a cylinder block, and heat transfer takes place from the hot gases inside the cylinder and to the ambient. And this model can be modeled using axis symmetry problem uh, using ANSYS tool, and we learn all steps in detail. First, create the geometry in ANSYS space claim. We have to create to model heat transfer from gas. Here is the gas is there, which is at temperature 700 degrees Celsius, and there is the ambient is there. Here ambient is there, ambient, and there, and this cylinder consists of multiple layer 1, 2, 3, 4, 5, and 6. Uh, and this cylinder has this 5 layer, and heat transfer is takes place from gas to ambient, and we want to find out temperature profile from gas to ambient using the CFD, because this is a uh, uh, axis symmetry problem. We can model as a 2D problem. This is a 2D problem, and cylinder height is 162 centimeter, and it has inner liner L1, L2, L3, L5, and each one has a thickness of 0.15 mm. Thickness is given, and we can model it as axisymmetric problem. We know radius, we know thickness L1, L2, L3, L5. These are liner to the inside of cylinder, and outside it is exposed to the ambient. Actual thickness is 9 mm thickness. This is the L thickness, and we have to find the effect of the liner on heat transfer from gas to the ambient. First, we have to create the geometry in 2D space. This side 2D sketch I have created in sketch mode. Just you take this line and draw as per dimension, and this 5 layer I created, and this is a 9 mm thickness of the cylinder. This is 9 mm thickness, and this is a gas and this is the liner. One, two, three. This is the gas, and this is the this is the thickness of the cylinder, 9 mm. And these three, this there are 5 layers of the liner, and heat transfer takes from gas to the ambient. And this is the extra domain I have considered it is as ambient, T infinity, and this is the gas. This is at 710 degrees Celsius. And heat transfer takes place this way, and you have to take domain this way. This will be as axis of the cylinder. If you want to do 2D axis symmetric problem in ANSYS, the x axis should be the x axis should be the axis of the cylinder, and this is the radius. and and if you want to if you want to solve this one, if you want to solve this one, then uh, if you want to solve this one, this should be in xy positive quadrant. If your y is positive, x should be positive. Then this problem will be solved. Once this is over, then you can measure it. In here we can create some name, workbench here. Definitely there is some gap is there, we can see here. Some gap is there, I think here. Now we can here combine here, just we can see here. Because some gap is there here. In then we can measure first side the solver for the fluent side. This is CFD, and you can check the first size, and you can give size, the element size, and after that we can give sizing to the each sizing. I have given sizing this one, and this one size I have given. This I have given sizing. Just we can give sizing this one. This I have given the same sizing, like 2 mm. Then this is also sizing given, and while giving a sizing, we can select size and bias. Just we can give this size here. We can define the bias. That means how much is changing from first element size to the second element size, and that ratio we can define this one. This is a ratio you can divide ratio x2 to the x1. If this is the x-axis, then how much is changing, that progression for the size we can uh, give by giving the bias factor here. Same thing here and here. Then after that we can give name, fluid gas, fluid ambient, solid 1, solid up. This is a cylinder. Layer 1, layer 2, layer 1, layer 2. This is solid layer 3. Solid layer 3. Then you can give name solid layer 3. This is a 1, second, third. This is 4. Solid layer 5. Sorry, this is the 4. You can give name as a 4, and this is you can use solid layer 5. This way, this I've created this 5 layer 1, 2, 3, 4, 5, and this is solid layer first, second, third, fourth, and fifth. Whatever extra is created, it should be deleted. And this is the you have to define this is as axis. You can define axis, and you can define this is a inner layer. You can this is a layer. You can how can select this create names selection. You can this is a wall insulation. You can this is as a bottom wall insulation. This is the top, and this way we have defined this single layer. We can define wall exposed to the ambient. This ambient cylinder wall. This way we are defined. I think everything is over. Here we possibly can also give layer inner layer. This is a wall inner. Yes, a solid one. Just give name. And now it is over. We can save the file project, and after it is over, then we can mesh it. Just mesh it. Let us see how can we create mesh. Mesh has been created, but this is not that much structured mesh. What we do feel. Here we want to create a mesh. We have to. This I think sizing is not given correctly. Just we clear the generated data. Just we see the mesh sizing. This is the same sizing, and this is also same size. This sizing. If you want to, you can use this sizing as this. We can create. This we can create generate mesh. And this we can also create generate mesh. Because this is not clear, there is some gap is there. See here, some gap is created. You can see this is a gap is there. Because there is some gap is there. Because of that, it has created this problem. Can hit delete. Move here. So, then we can pull here up to this axis. Then we can split your body. Hmm. Then I have modified the geometry. And then you can see here, change the geometry. Here, change. Select this one, this one. a fluid ambient. First check the mesh we are able to or not. If mesh is okay, then you can union. See here is the interface is there. See here. Here no mesh is created, interface is created. No mesh has been created. Just we can use this all body, this body, this body, this body, this body, this body, this body, this. You can give this one on option is you can keep all this in one surface. You can create a new component. You can use a share table. Here I have to use the share. If I use share here, and then you can see here. I think this has been changed because you have to change your share. Then you can see how it is happening. See, this is how happening. You can check this. Yes, we can see here. You create in the sun. One, two, and yeah, this is 9. Then you can say here, select here this one, this one, this one, this one, this one, this one, these two, this one, and this I think is not required. You can simply delete. This is the pure gas selection of the gas. This is the fluid ambient. This is the layer 6. This is the layer 1, layer 2, layer 3, 4 layer. This is the axis, the layer axis. This is important. This should be given. This is the mass cylinder. This is ambient. The inner gas cylinder. This is the inner. This way we can save project. Now mesh. You can see how mesh will be created. See how mesh will be created. It should be structure mesh. Now this way mesh is created. And this I will write 1. This is write 2. 1. This is the 1. This is the 1. See mesh will be created. This way mesh will be created. If you want to create boundary layer, there is an option is there. Once meshing is completed, you can save the ANSYS workbench file in your project folder, and then we can see here the mesh file has been saved, and please note the path, and that path should be copied in the ANSYS Fluent directory, and select the 2D solver and open the ANSYS Fluent launcher. Once ANSYS Fluent launcher is open, then you can read the 2D file. Please note that we have done meshing in 2D, and we should read 2D file and read the mesh file. Here you can see the mesh file has been read, and it shows the warning that we have selected axis in uh, meshing, and you should select axis symmetric steady state pressure based solver, and gravity should be in the x direction because fluid flow vertically in x direction. Axis is in x direction. For axis symmetric case, x axis should be the axis of the our problem. This is our computation domain. This is the x axis. This is the y axis, and these are the layers. Please note that we should solve in axis symmetry case, and select here to display the mesh. This is the mesh. We can hide the node and see the mesh. And once mesh general setting is okay, then give the boundary condition. Ensure that all the names given in the meshing should be reflected in the ANSYS Fluent solver. If any name is missing, you can go back to the ANSYS workbench meshing mode and name and again export and read here for the Fluent solver. Please ensure that all the layer of ICNG cylinder should be displayed here, and you should be able to solve this problem. Make sure ensure that all the layers have been selected, and name should be given. Name of all the boundary conditions should be given properly here, and make sure that all the layers of hot cylinder or liner should be reflected here. This is the problem of IC engine liner, and it should be reflected here, and give the name what you want, and there should be pressure inlet and outlet so that you can give boundary condition properly, and pressure far field cannot be coupled if you want to combine with V. It may show some error. You can give pressure inlet and outlet. Pressure far field you can replace as symmetry boundary condition, and these are some wall boundary condition. You have to give name. I think this is the pressure boundary. Because we didn't give name in the ANSYS workbench machine, hence it shows the default as wall, and we can give pressure boundary. You can select in the ANSYS Fluent. It is not a problem, and here select the pressure outlet boundary. You can select the pressure inlet and outlet as per your convenience, and apply it, and make a gauge pressure to be 0. Similarly, you can define as a pressure inlet here. Then you can define here. These are the pressure inlet and outlet boundary condition, and show in display option so that we'll understand properly, and save the case file as run1. Once file is saved here, ensure that we have given the proper thermal properties of the each layer. There are 5 layers, L1, L2, L3, L4, L5, and each layer has different conductivity, and we can check the property that are given properly, and see there are some fluid zone inside the cylinder and outside the cylinder, and you have to define the material. Default there is aluminum, but you can define the 3 material. There is some material solid one, and you can define the conductivity. Then you have to enable energy equation. Then it will show the, and make sure that chemical formula should be different so that the material property should be written separate, and make sure that energy equation should be enabled. Then only we can see the thermal property like conductivity and specific heat, and give this property properly, and we can define the property what you want. And once properties are defined similarly for the other layer, then we can see here, and similarly define the solid zone, and make sure that we have given the material property to each zone, and here is given for the outside and inside flue gas temperature to be fixed, and here you can go to the fixed value. You may go to the some value if you want to go fixed value. Source term we don't need to, I think, define. Energy is not required because we are not giving any heat flux. That is not required. I think this is not required. Uh, I think this is the energy source, but I think it's not required. Here, you select the solid zone, uh, particularly decide the fluid properties, and whatever property given, I have And then you can set the run. You can use a study solver. Keep energy equation on. Use the material fluid. This air. Solid property. Define conductivity. You can use property as you require. And then also define other material. Then we can define a cell zone property to each material. You can select the material here, material 6. For gas, we can define fixed temperature 7 on C. That means you can define as 983.15. That means you can define temperature of the 710 degrees Celsius. You plus add to 73.15, and then you can get a value 983.15 Kelvin. Yes, we can define temperature here 9. And then you can define a control method as a simple and boundary condition. We can define this is axis, this is axis, and this is axis. This is a pressure bottom, this is a pressure top. This extreme boundary condition you can define as the symmetry or pressure outlet, because pressure outlet won't work here because there are three boundary are here. We can define as a symmetry, and these are all boundary condition here. This way we can initialize and then we can iterate. You can see the convergence, it is running well. And then you can control C stop, and don't forget to give this bond this what operating condition. This operating condition is should be given. Now can see the temperature. See how temperature is coming. If I use the symmetry boundary condition, then you can see the temperature control like this one. Because this cold air is there and it is heating. Then you can see the temperature is like this way, and you can save the file. Write case data and save the file. You can see the temperature here is, and you can also try boundary condition here. You can define symmetry or pressure outlet. You cannot define. because I give as a 0 gradient boundary condition. Hence it's coming here. You can take temperature is 675 here, and here temperature is very high. This way you can the same problem I have been refined here. We can go to the physics. No, you can go to domain, and here go to the adapt, and here is the option is there, and we can register here cell. We can here register cell for the new region, and that will be named here region 1 0 region 0, and here is option is there adaptation rule, and here I have adapted by cell by 3 times, because once original mesh which contain cell around 6000, after adaptation it will be around 14,000 plus cells will be there, and once we do adapt, and we can see the here mesh number of cells have been increased. This intersolid, and this is the intersolid one. There are 5 layers are there. The 1, 2, 3, 4, and 5, and then this is the outer layer, and this is a gas, and heat transfer takes place from hot gases to the surrounding. This have been meshed here. Then after that, just run it. We can yet just run it. We can find out simulation has been run, because this is a run only for the velocity, energy, and turbulence. This is run for mesh N1, and this is the mesh run for mesh N2. After running, we can see the result. Then you can see we can calculate here how it is being calculated, it being run. Then you can see the result here. And we can see the how result is looking like here, and here are different layers are there. We can see here XY plot, and we can see this plot how is created here. See this what I draw the straight line here, draw the line across the E. This line I have created, this point first, and this is second point, and this see the how is the temperature variation. This is a temperature variation will be there, and this how I created. We can go here result and create a line. Then here a line will be created here. Just we give the name. Then how we will find out? Then we can see the here scale here. Using the scale, we can create a line here. Just we can take line here center 0.08, 0.008, and give y minimum as 0, and y max will be given as a 0.085. then this line will be created here. Take x fix and then line will be created here, and then you can see how plot will be looks like here. This is the line, this is the plot, this is the hot gases, and this is the ambient, and we see how much temperature gradient is there, that we can see here. And we can also write the file. Here is the option is there, write file. Then we can also file here 2D temperature plot, 2D temperature xy plot. It's called as xy plot. This way you can post process and in Excel and present in your report. Thank you for watching this video. Subscribe this channel for more update related to this, and visit the site CFD Flow Engineering for all problem related to CFD. Thanks. Thank you for attending this lecture. For more information about CFD analysis of any problem using ANSYS, Fluent and OpenFOAM, you can visit website www.com CFD Flow Engineering. It covers most of important topic for engineer scientists related to the CFD and flow engineering, and also covers topic for flow technology. Thank you for attending this lecture. God bless you.